decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
For nearly 5 decades, the Voyager probes have quietly streamed data from the edge of the solar system.
NASA's Voyager 2 spacecraft has been sent back its first message from interstellar space,
Revealing worlds, radiation belts, and the very nature of interstellar space. But recently, Voyager 2's readings and Voyager 1's unexplained signals have defied expectations, hinting at anomalies that challenge decades of scientific understanding.
Voyager 1 probe is sending usable information to Earth again.
What these final transmissions reveal may rewrite our knowledge of the universe or uncover mysteries humanity is only beginning to grasp. The Uranus mystery. Nearly 4 decades after Voyager 2 swept past Uranus and sent its final transmission of the planet back toward Earth, scientists believe they have finally uncovered what lay behind one of the mission's most baffling readings. At the time, the anomaly stood apart from everything the spacecraft had observed before, and for years it remained unexplained, suspended between speculation and uncertainty. Voyager 2 reached Uranus on January 24, 1986, passing within 81,500 kilometers of the planet's cloud tops during its only visit. The encounter revealed a world unlike any previously explored. Uranus rotated on its side, tilted at an extreme angle, with seasons that lasted decades and sunlight striking its poles in ways no other planet experienced. Its magnetic field was misaligned with its rotation, twisted into a strange geometry that stretched far behind the planet in a long helical tail extending millions of kilometers into space. As Voyager 2 moved through this distorted magnetic environment, it collected a wealth of data. It discovered 11 previously unknown moons, mapped a ring system unlike those of Jupiter or Saturn, and captured detailed images of icy worlds such as Miranda, whose vast canyons hinted at a violent past. Beneath a veil of atmospheric haze, enhanced images revealed concentric cloud bands circling the South Pole, while ultraviolet emissions known as day glow radiated unexpectedly from the planet's upper atmosphere. Temperatures across the planet remained remarkably uniform, with little difference between sunlit and dark regions. The spacecraft also detected lightning deep within Uranus's atmosphere, powerful but hidden beneath thick cloud layers. These electrostatic discharges released enormous bursts of energy, lasting only fractions of a second, yet rivaling lightning on Earth in strength. Together, these discoveries painted a picture of a cold, distant planet that was nonetheless active, dynamic, and deeply complex. Yet it was Voyager 2's final radiation measurements that caused the greatest confusion. As the spacecraft passed through Uranus's magnetosphere, its instruments recorded an electron radiation belt far more intense than scientists had predicted. Based on everything known at the time, Uranus should have possessed a relatively weak radiation environment. Instead, Voyager encountered energy levels that rivaled or exceeded those seen near much larger planets. The readings did not align with existing models, and no clear mechanism could explain how Uranus sustained such a powerful concentration of trapped electrons. For years, the anomaly remained unresolved. The prevailing assumption in 1986 was that high-frequency electromagnetic waves detected near the planet would scatter energetic electrons, causing them to fall into the atmosphere and weaken the radiation belts. Voyager's data appeared to contradict that logic, but there was no alternative framework to explain what it had seen. Decades later, advances in space physics reshaped how scientists interpret such environments. Researchers at the Southwest Research Institute revisited the Voyager 2 data with modern understanding and reached a striking conclusion. The spacecraft may have arrived at Uranus during a rare and intense space weather event. Their analysis suggests that a large solar wind disturbance was moving through the Uranian system at the time of the flyby. Known as a co-rotating interaction region, this structure forms when fast solar wind streams collide with slower ones, compressing plasma and magnetic fields as they travel outward from the Sun. Near Earth, similar disturbances are now known to dramatically energize radiation belts, rapidly accelerating electrons instead of dispersing them. To test this idea, scientists compared Voyager 2's Uranus measurements with detailed observations of a major solar wind event recorded near Earth in 2019. During that event, powerful electromagnetic emissions called chorus waves emerged, driving intense radiation belt acceleration. When Voyager's Uranian data was re-examined through this lens, it showed consistent signatures of the same process at work. This reinterpretation transformed the meaning of Voyager 2's final readings. Rather than revealing a permanent feature of Uranus, the spacecraft may have captured the planet during a brief but extreme episode when external solar forces temporarily supercharged its radiation environment. The high-frequency waves detected during the flyby, once thought to drain energy from the system, now appeared capable of injecting it instead. The intensity of these waves ranks among the strongest recorded anywhere during Voyager 2's entire mission, signaling that the spacecraft had crossed not a calm boundary, but a region briefly charged with extraordinary energy. Seen in this light, Voyager 2's encounter with Uranus was not a flaw in the data, but a rare moment of timing, one that captured a transient event and reshaped scientific understanding long after the signals faded. Yet those revelations were only the beginning. The mysteries of interstellar space. After completing its planetary encounters, Voyager 2 entered an extended interstellar mission, focusing on conditions beyond the heliosphere. NASA continued to use the spacecraft to study the outer boundary of the solar system and its interaction with interstellar space. By September 2023, Voyager 2 was still transmitting scientific data at a rate of approximately 160 bits per second through carefully managed telemetry exchanges. In 1990, Voyager 1 captured a family portrait of the solar system, producing the now iconic image of Earth known as the pale blue dot. Shortly afterward, its cameras were deactivated to conserve power and computer resources for other instruments, and the software controlling them was removed, making reactivation nearly impossible. Despite this, Voyager 1 continued its mission, providing insights into the heliosphere, the solar wind, and the transition to interstellar space. As it traveled outward, Voyager 1 surpassed Pioneer 10 to become the most distant human-made object from Earth, moving at roughly 17 kilometers per second. It continued to study the environment around the solar system, using plasma wave instruments to investigate the heliopause, the boundary where the solar wind gives way to interstellar space. Along the way, it crossed the termination shock, where the solar wind slows to subsonic speeds, and then entered the turbulent heliosheath, marking the Sun's waning influence. Voyager 2 also contributed to astrophysical research after its planetary mission. In 1992, it observed the Nova V1974 Cygni in the far ultraviolet spectrum, marking the first measurements at those wavelengths and providing detailed data on the nova's brightness variations. In July 1994, Voyager 2 was positioned to observe the impacts of Comet Shoemaker-Levy 9 on Jupiter. While its location offered a direct line of sight in ultraviolet and radio frequencies, the fragment's fireballs fell just below the spacecraft's detection threshold. The spacecraft also engaged public interest. In 2006, amateur radio operators in Germany tracked Voyager 1's signals, confirming the data transmitted through NASA's Deep Space Network and demonstrating the far reach of human exploration. Operational challenges increased as the spacecraft aged. On November 29, 2006, a telemetered command was misinterpreted by Voyager 1's onboard computer, activating magnetometer heaters for several days and causing temperatures to exceed design limits. Voyager 2 crossed the termination shock on August 30, 2007, entering the heliosheath roughly 1 billion miles closer to the Sun than Voyager 1, highlighting the heliosphere's asymmetrical shape caused by interstellar magnetic pressures. In April 2010, Voyager 2 experienced a data formatting problem caused by a single flipped bit in its onboard computer. Engineers scheduled a reset in May, which restored normal data transmission within days. By 2010, Voyager 1 had passed the radial reach of the solar wind, with interstellar pressures beginning to dominate its environment. A major maneuver in 2011, rotating the spacecraft 70 degrees to measure lateral solar wind motion, was executed successfully using Alpha Centauri as a guide star. Voyager 1 then observed phenomena not previously recorded, including Lyman alpha radiation from the Milky Way and regions where solar particles slowed while interstellar electrons increased. By mid-2012, it approached the heliopause, and later that year, at 121 astronomical units from the Sun, Voyager 1 became the first human-made object to enter interstellar space. Confirmation required months of analysis, including plasma density measurements triggered by solar activity. Voyager 2 followed a similar path. In 2013, scientists anticipated it would cross into interstellar space within a few years, with its plasma spectrometer providing the first direct measurements of plasma density and temperature. A defining change in magnetic field direction was not immediately observed, but by November 5, 2018, Voyager 2 also crossed into interstellar space, offering complementary measurements of plasma density, temperature, and magnetic fields. Scientific discoveries continued to emerge from the Voyager probes long after their planetary missions ended. In October 2020, researchers identified an unexpected rise in particle density beyond the solar system, detected independently by Voyager 1 and Voyager 2. The observations indicated that this density gradient is not a local irregularity, but a large-scale feature of the very local interstellar medium, most pronounced in the direction of the heliospheric nose. As Voyager 2 extended its reach, it crossed a symbolic threshold on July 18, 2023, overtaking Pioneer 10 to become the second farthest spacecraft from the Sun. Yet even as scientists worked to interpret the steady flow of data from the Voyagers, a separate transmission from Voyager 1 introduced a new uncertainty, one that sent researchers urgently re-examining assumptions about the behavior of humanity's most distant spacecraft. Voyager 1's shocking transmission. Recently, the Voyager mission entered an unexpected period of uncertainty. Voyager 1's long, reliable transmissions abruptly changed, shifting from structured scientific data to uninterrupted streams of binary code. The signal still arrived on schedule, but it no longer carried interpretable information. Suzanne Dodd, NASA's Voyager project manager, confirmed that the spacecraft had stopped communicating in its normal operational mode. Engineers first focused on the most likely cause: failure within Voyager 1's aging onboard computer. Working within the limits of hardware designed in the 1970s, the team prepared careful reset commands and corrective instructions. Each command took nearly 2 days to reach the spacecraft, and each response failed to restore normal function. As the attempts continued without success, it became clear that the issue was not a simple system error. Although NASA publicly described the event as a technical malfunction, the nature of the signal prompted closer scrutiny. The Deep Space Network verified that the transmissions were genuine and consistently received by antennas around the world. The signal was stable, repetitive, and internally ordered, characteristics that ruled out background noise or random interference. Scientists classified the behavior as an anomalous frequency event, acknowledging that it did not fit established failure patterns. Within the mission team, concern grew steadily rather than dramatically. The data did not appear random, yet it also did not correspond to any known operating state of the spacecraft. Linda Spilker, Voyager's project scientist, noted that the rhythm within the signal suggested internal structure, even as official assessments continued to treat the problem as a consequence of extreme age and distance. That concern broadened months later when Voyager 2 experienced its own disruption. In August, the spacecraft's antenna drifted out of alignment, interrupting communications from more than 12 billion miles away. Contact was lost for several days before a weak signal returned, indicating that the probe remained functional but unstable. The timing of the two incidents, while not conclusive, drew attention because of their proximity. Around the same period, Voyager 1 exhibited another unexpected behavior. Without receiving any command from Earth, the spacecraft adjusted its orientation slightly, altering its trajectory in a way that could not be linked to known external forces. At the same time, its instruments detected a low-level signal resembling the hum Voyager 2 had recorded years earlier. Shortly afterward, Voyager 1 reoriented itself toward an empty region of space, lacking identifiable stars or planetary bodies. In conjunction with this shift, systems that had long been inactive briefly responded, despite having been powered down for decades. The behavior suggested an internal reaction rather than an external command, though the cause remained unclear. As these events accumulated, explanations became increasingly constrained. Some engineers proposed that long-term radiation exposure may have reactivated dormant sections of code, producing unexpected system responses. Others suggested that the spacecraft was responding to internal signal feedback in ways not anticipated by its original design. While no evidence supported deliberate external influence, the sequence of behaviors resisted simple classification. NASA continues to review archival documentation and original software. Are these events caused by the gradual degradation of aging spacecraft, or the first signs of something reaching back from outer space? The anomalies and transmission errors. Some scientists attribute the unusual behavior observed in both Voyager spacecraft to gradual degradation within their onboard computer systems. Each probe carries 3 flight data system computers that gather measurements from scientific instruments, monitor spacecraft health, and route information through the telemetry modulation unit for transmission to Earth. This system operated reliably for decades. But more recently, the data stream began looping into unreadable patterns. Engineers traced the issue to the flight data system, although the precise cause of the malfunction could not be determined. Initial recovery efforts followed standard procedures, including shutting down and restarting the affected system. These attempts had no effect, reflecting the difficulty of maintaining hardware designed in the 1970s. Troubleshooting now depends on partial documentation and long-retired engineering practices, while accounting for components that have functioned far beyond their intended service lives. Earlier disruptions helped frame the challenge. In 2020, maintenance upgrades to the Deep Space Network suspended outbound communication with Voyager 2 for 8 months. Contact was restored in November through a carefully sequenced set of commands, and full communications resumed in February 2021 after a major antenna upgrade. Although the spacecraft itself was unaffected, the interruption underscored how vulnerable the mission had become to limitations on Earth. In May 2022, Voyager 1 transmitted telemetry that deviated from expected parameters while remaining operational. Engineers traced the anomaly to the attitude articulation and control system, which was functioning correctly but sending invalid data. Further analysis showed that the system had been routing information through a long-dormant computer, corrupting the signal. By August, engineers corrected the problem by redirecting data to an alternate onboard computer, restoring normal telemetry, though the trigger for the original switch remained unresolved. A separate issue occurred shortly after Voyager 2 surpassed Pioneer 10 in interstellar space. A programming error caused its high-gain antenna to tilt 2 degrees away from Earth, interrupting communications. Engineers detected the spacecraft's carrier signal by August 1st and restored contact on August 4th by transmitting a high-power command from the Canberra station. Although Voyager 2 was programmed to autonomously realign itself if needed, the prompt correction prevented a prolonged disruption. More serious difficulties emerged on November 14, 2023, when Voyager 1 began transmitting sequences that could not be decoded. By December, NASA confirmed that the flight data system could no longer communicate with the telemetry modulation unit, halting scientific data transmission. Engineers traced the failure to a damaged memory bank, likely affected by long-term exposure to high-energy particles or cumulative wear. Despite unsuccessful reboot attempts, Voyager 1 continued responding to commands and maintained a steady carrier signal. Because the damaged memory could not be repaired, engineers relocated essential software to intact sections of the spacecraft's 68-kilobyte memory. This process required removing obsolete routines tied to earlier mission phases to free space for critical functions. By April 2024, these changes restored limited data transmission, allowing 2 of the 4 scientific instruments to resume operation. Further adjustments followed, and by June, all 4 instruments were transmitting data again. Even then, operations remained sensitive to secondary system responses. Operations remained sensitive to secondary effects. In October 2024, an automated fault protection response shut down Voyager 1's primary X-band transmitter after a heater was activated. Communications temporarily shifted to the S-band transmitter, which had not been used since 1981. Engineers monitored the system closely and restored the primary transmitter by mid-November, allowing normal operations to continue. At the same time, mission planning was complicated by upgrades to Deep Space Station 43 in Canberra, the only antenna capable of sending commands to both Voyager probes. With communication windows restricted, engineers worked within tight schedules to reactivate backup roll thrusters and ensure continued control before the station became unavailable. Throughout these challenges, the flight data system has remained central to the spacecraft's survival. Composed of 3 interconnected computers, it manages scientific data, tracks spacecraft health, and supports communication with Earth. While it performed these tasks reliably for decades, the combined effects of age, radiation, and distance now demand careful management. Each adjustment requires precise planning, familiarity with obsolete systems, and patience shaped by signal delays that approach a full day. Despite these constraints, Voyagers 1 and 2 continue to operate within stable limits. For now, they are under control. But how much longer can they survive? The final lap. As the power from Voyager 2's radioisotope thermoelectric generator gradually declines, NASA has systematically reduced the spacecraft's energy consumption, turning off instruments one by one. The first to be powered down was the Plasma Science subsystem in 1991, saving just 1.2 watts, but marking the beginning of a decades-long process of conserving resources. Over time, additional systems were deactivated as power became increasingly constrained. In 1998, the scan platform and ultraviolet spectrometer were turned off, followed by the digital tape recorder in 2007 after the earlier failure of the high waveform receiver on the plasma wave subsystem in 2002. The planetary radio astronomy experiment was powered down in 2008, and heaters for the cosmic ray subsystem and the low-energy charged particle instrument were turned off in 2019 and 2021, respectively. Software updates in 2023 rerouted power from the voltage regulator to sustain the remaining instruments. Yet the Plasma Science instrument was retired in 2024 and the low-energy charged particles instrument in 2025. By around 2030, Voyager 2 will no longer be able to power any scientific equipment, and by 2036, it will be out of range of the Deep Space Network entirely. Managing the spacecraft's orientation has also grown more challenging. Several thrusters critical for pointing the high-gain antenna toward Earth have become clogged due to hydrazine buildup. With no backups remaining, the mission now operates entirely on single-string systems. NASA has developed software updates to modify the behavior of the remaining thrusters, slowing the clogging of the small-diameter hydrazine jets. These updates are first tested on Voyager 2, which remains closer to Earth, before implementation on Voyager 1. In September 2024, a thruster swap shifted control from clogged thrusters to a less used set idle since 2018. And by May 2025, backup roll control thrusters, dormant since 2004, were successfully revived. Voyager 1 faced similar challenges. In December 2017, NASA activated all 4 of its trajectory correction maneuver thrusters for the first time since 1980 to replace degraded jets and keep its antenna pointed toward Earth, extending the spacecraft's ability to transmit data for an additional 2 to 3 years. As with Voyager 2, engineers prioritize the operation of instruments most likely to return critical data on the heliosphere and interstellar space, turning off non-essential equipment to conserve energy. Beyond power and thruster limitations, both Voyagers operate on computer systems designed nearly 50 years ago, long before the era of personal computing. Each spacecraft carries three main computers. One monitors the spacecraft's health and temperature while coordinating the other two. A second manages orientation, firing thrusters to maintain antenna alignment, and a third stores the stream of scientific data and images. Together, these computers contain just 70 kilobytes of memory, roughly the size of a single modern digital photograph. The Voyager's memory is uniquely resilient. Bits are stored using plated wires and thin metal plates, with each intersection representing a 1 or 0. The state remains even without power, making the system durable across decades. To conserve space, engineers programmed pseudocode routines to carry out repetitive tasks efficiently. Updates are written in assembly and Fortran, converted into machine code, and transmitted across billions of miles at 16 bits per second. Upon arrival, the instructions interrupt the computer's routine, install the update, and then resume operation. These carefully executed updates have kept the spacecraft operational. In 1995, engineers installed code allowing the spacecraft to restart certain systems autonomously if failures occurred. 20 years later, this capability allowed Voyager 1 to recover from a hardware malfunction. In 2010, a single flipped memory bit disrupted the internal clock, delaying commands by 2.5 hours. A targeted update corrected the error, restoring normal timing. These interventions demonstrate the patience, precision, and ingenuity required to maintain hardware decades beyond its expected lifespan. Thruster and software maintenance remain critical. Every use of hydrazine leaves minute deposits that gradually restrict flow, threatening the spacecraft's ability to maintain orientation and communicate. Because Voyager lacks an operating system, its memory contains only raw instructions, etched as 1s and 0s. Updates, even minor ones, must be carefully constructed and transmitted across vast distances. For example, after Voyager 2 passed Neptune, engineers rewrote camera routines to take longer exposures in dim light, then later shut down the cameras and other instruments to conserve power, extending the spacecraft's operational life. Despite these constraints, Voyagers 1 and 2 continue to explore the outer reaches of the solar system and interstellar space. Voyager 1 now lies approximately 15.1 billion miles from Earth. Engineers at NASA's Jet Propulsion Laboratory, under project manager Susie Dodd, monitor the spacecraft closely, analyzing decades-old records and managing delicate operations to maintain orientation, recover thrusters, and sustain limited instrument functionality. Each command requires patience and precision, as signals take nearly a full day to reach the spacecraft and an equal time to return. Looking far into the future, Voyager 1 is expected to remain in the outer solar system for tens of thousands of years. In roughly 300 years, it will reach the theorized Oort cloud, traversing it over 30,000 years. Though not aimed at any particular star, it will pass within 1.6 light-years of Gliese 445 in about 40,000 years, and within 1 light-year of the M3V star TYC 3135521 in roughly 300,000 years. Voyager 1 benefits from multiple planetary flybys that boosted its velocity, a trajectory advantage not shared by probes like New Horizons, which travel more slowly and decelerate more rapidly due to solar gravity. NASA describes the Voyagers as destined, perhaps eternally, to wander the Milky Way, continuing their journey long after their mission teams are gone. Through these challenges, the Voyagers demonstrate not only the resilience of their design, but also the extraordinary skill of the engineers who maintain them. The gradual decline in power and mechanical capability is met with careful planning, inventive software updates, and precise control of aging thrusters. The spacecraft's computers, memory systems, and instruments, though minimal by modern standards, continue to deliver valuable scientific observations, revealing conditions in the heliosphere, interstellar space, and beyond. Even as Voyagers 1 and 2 approach the limits of their power and communication, they remain active participants in exploration, silently transmitting measurements of particles, magnetic fields, and cosmic radiation from the edge of human reach. Each new data point extends our understanding of the solar system and interstellar space, providing insights that would otherwise remain inaccessible. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.